In this video, we'll discuss the depression produced in a beam. So let us suppose that there is a beam of length L and this is depth D and its breadth is B. You can see the cross-sectional view of this beam, and this beam is supported by these two supports, and this beam is depressed by some length due to its own weight W. So in this case, you can see that W will be the weight which will be depressing this beam in the downward direction. And you can assume that to find this depression, in fact, let us suppose it is del. So we can assume that this is one cantilever which is having a hinge here, and this is the cantilever like that. And its weight would be W by 2, obviously. We are talking about half part, and its length will be L by 2. And for another similar cantilever, the depression will be same. So you can find out this depression by either of them. So you can see that we have already discussed that in cantilever, the depression in cantilever was equal to, we have already discussed that it was equal to WL cube divided by this one. You can see that WL cube by gamma Ig into 3. So this is gamma. Young's modulus. Ig is the geometrical moment of inertia, and into 3. Now you can see that for this single cantilever, del will be equal to W, which is W by 2, and L, it is L by 2. So it is, and this is 3 gamma Ig. So you can see that it would be W L cube by 48. This is 8 into 2, 16, and 16 into 3 is 48 gamma Ig. So this is the depression in the beam, which is WL cube by 48 gamma Ig. Some of you must be wondering that why I have not added that depression due to both cantilevers. This is, you can observe that this depression would be same due to both cantilevers. So you can find out this depression by either of them, and this would not be added because they are not adding up the depression. So you can find this, in fact we can say that this depression would be same for both cantilevers. So you can find out this depression by either of them. Now if beam has a rectangular cross section area, this is rectangular cross section area, whose width is equal to B and whose depth is equal to D, then Ig for such a beam, which is geometrical moment of inertia, is B D cube by 12, where B is breadth, which I have already explained in the previous diagram, this one, and D is the depth of the beam. Okay, so delta for this rectangular beam will be equal to WL cube by, this is 48 and gamma into Ig. Ig will be BD cube by 12. So you can see that it is equal to WL cube by, this is 4 gamma BD cube. Now if this beam is of cylindrical shape, then its cross section would be cylindrical, and therefore for a beam of cylindrical cross section, you can see that the cross section area or the geometric moment of inertia would be pi r to the power 4 by 4. Therefore, we can say that for this cylindrical beam, delta depression will be W, this is L cube by 48 into gamma Ig. Now we can write down the value of Ig here as 48 gamma, and Ig will be pi r to the power 4 by 4. So it would be equal to W L cube divided by this is 12 gamma into pi r to the power 4. This is for cylindrical beam. Okay. So this is the depression produced in the beam. Now in next video we'll discuss the significance of I-shaped beams. Thank you. In this video we'll discuss the significance of I-shaped beams. Now first of all, let us see that there is a normal beam whose this depth is D and whose this length is L and whose breadth is measured inside the plane, which is B. So we have already derived the result that the depression produced is this one. This is, you can see that it is omega L cube by 4 gamma BD cube. This is weight of the beam, this is L length and 4 gamma Young's modulus, and B is the breadth and D is the depth. Okay, so you can see that in this case D is small and L is large. So if if we increase L and if we decrease D, then in both cases del will increase. So for same weight, this beam will bend more because its depression is larger. Now if we use a beam of smaller length, this length, and greater depth, then you can see that the del, let's suppose the depression in this beam is delta 1 and in this beam is delta 2. So you can see that we have decreased this length and we have increased this depth. So by decreasing the length and increasing the depth, del will decrease quite significantly, and therefore delta 2 will be very less than delta 1 for the same load. If we are loading with the same load, let's suppose we are applying a same load W on both of them. So this beam will be bending very least. Now therefore, you can see that this type of section is more useful, that it can bear a greater load without bending. So this section is used in this beam. Now why this I sections are used? This is called as flanges. These are flanges. I am writing it down that these are flanges and this is web. So we are using this web as this beam, and these are the flanges. The use of these flanges is the fact that when some load is applied on this section, then you can see that due to the greater area of this section, the stress developed by the same load is very less. So that stress is transferred to this beam, and this stress is very small due to the greater area of cross section, and therefore this web is experiencing a less stress, and therefore it can bear more load. So due to this fact, this I-shaped beams, which are also called as girders, are used in buildings or bridges, and you have already seen that the railway tracks are also of I-shaped to bear the heavy load of the trains. So this is the concept of I-shaped beams. Now with this video, we are done with elasticity, and in the next section I will be bringing thermodynamics videos. Thank you.